Hello, this is the Datumate Live Webinar series, DatuGram 3D in Action, turning a regular camera into a surveying and mapping tool. My name is Eric Colburn. I'm a professional land surveyor and president of Colburn Strategic Partners, and this webinar is being hosted by Datumate. So, quick note, we are having a blizzard weather event. You might have gotten an email on that about an hour ago. So if we do lose power or there is some sort of interruption, we have a couple of options. First of all, we'll definitely reschedule and finish up whatever we don't finish here today. But I also took some time yesterday to pre-record this in case that happens, and what I'll do is email you a link to that recording if necessary. But so far, snow's still coming down, the wind's quieted a little, knocking on wood, and I think we'll be okay. If you have any questions, again, please feel free to use the chat option and ask questions. I will try to look at them every once in a while to see if I can pick up on your questions, and if not, we'll definitely do a review of the questions come the end of the webinar. I'll stay on air for a while to answer your questions. And you can also always just reach out to Datumate or myself, and we'd be happy to answer any questions that you have. So again, this is the DatuGram 3D in action. We're turning a regular camera into a surveying and mapping tool. So a little bit about Datumate. They are a leading vendor of field to plan software products. They have hundreds of customers, mostly land surveying firms in Israel, Europe, and the United States. Dr. Jad Jarouche is the founder and CTO. Chaim Zelikovsky is the co-founder and CEO. And as I mentioned before, I'm Eric Colburn, president of Colburn Strategic Partners. One other note, we are recording this, so it will be available after the webinar to be viewed. So the outline of this webinar is we're going to see DatuGram 3D in action, working with real data collected in the field, and we'll be using just some regular high-resolution camera images, a little bit of ground control points in a form of a coordinate file, and then we'll be processing a complete data set from beginning to end, and we'll do some surveying and mapping using DatuGram 3D. And we'll be walking right through what's a rather intuitive user interface, which you will see. We will learn about the latest technology in close-range photogrammetry. And specifically, I want to talk a little bit about how to use and what to look for in a camera for surveying and mapping. So, because of the time constraints on this, what I am doing in the background is, before I started the webinar, I created a brand new DatuGram 3D project. Let's see if we can look at that. Hold on 1 minute. Okay, and you can see it's almost done. So what I did, we'll go over this in a minute. I want to go over a little bit of the field work and the camera content first, but I just wanted to show you, because of the amount of time that it takes to process the images and link them together, that I started it about 10-15 minutes before the webinar started, and I brought in 19 images, which we'll review when we get to that point, and I've selected a camera calibration, and we're linking those together, and it looks like it has about a few more minutes to go before it is done. Okay, so that's working in the background while we're going through the webinar. So the agenda for today's webinar is we're going to review field procedures and data. We're going to look at cameras, how does it work in selecting a camera, and then we'll literally be going through the workflow of DatuGram 3D. We'll start with images, loading and linking, which I just showed you a little bit of. We'll georeference by importing the control file, and we'll anchor those images. We'll do some measuring and drawing, creating 3D entities. And that's really the bulk of what we'll be doing, but I also want to go over the final two workflows in DatuGram 3D. which is approving, checking, and improving your work. View and export, we'll look at views, reports, and CAD integration, and then we'll wrap it all up. Okay. You know, if we look at surveying today, it's a very expensive, labor-intensive, can be complex and error-prone types of work. We're making field measurements, sketching in field by hand, and then somebody in the office is trying to take and combine that data, being your coordinate files or your field notes and your sketches, and turning that into drawings of maps and plans. And with close-range photogrammetry, we're looking at a brand new field-to-plan process using regular cameras, which is very cost-effective, simple, and highly accurate. And we're looking at a simple three-step process, if you will, starting from left to right. We'll be shooting the photographed area that we want to survey. We'll take some images. We're going to georeference the images and we're not taking surveying out of the process here. We have to do some surveying in the field to locate some ground control points to be able to identify those on the images. And then we're going back in the office and we're drawing directly on those images to get full 3D values. So again, a little bit different than probably what you've seen before. We're going to be using two-dimensional images, if you will, and draw directly on them. And the value of that is that there's no need for digitization or stereoscopic views or expensive equipment to do that. The user can draw those objects directly on the images with full 3D result. And we're going to get 3D positions of those new points and objects that we're drawing that are going to be automatically found in real time by the software. And we'll go through and show you that with some actual drawing. Let's look a little bit about the photography that has to happen here. So a couple of key things, and this may seem simple, but it's really an important factor to consider, is elevating the camera above ground level to minimize foreground obstructions. If we cannot see the object in the image, you cannot map it. It's as simple as that. And as you'll see in a slide coming up, it actually has to be seen. Any object that you want to map or survey has to be able to be seen in 3 images. So we want to take photographs from an elevated vantage point, if at all possible. And that can be from the rear of a truck. We can get on the roof of a building or out on a stoop of a building and take maybe pictures of an intersection, for instance. And a very effective methodology is using a telescopic pole. And then I think the best way to do it, obviously, is using a mini quadcopter, because it's very fast at capturing a lot of data, and we can cover a lot of ground quickly and easily and get probably the best height that we can so that we can minimize foreground obstructions. So a key factor when we do take those images out in the field is we want to slightly vary the camera's elevation for each image. And this will ensure optimal measurement accuracy. DatuGram 3D is all about angles and the different types of angles that we can form, either between different images, not only if we're looking at images left to right, if you look at the cameraman here holding the camera, but also by varying the angles, by raising and lowering the camera slightly, helps to add different angles and gives us different redundant measurements to each point as we work. Another key factor to keep in mind is that we want to take our images in consistent lighting conditions. So we want to make sure that all those images have very similar lighting conditions, and that pretty much means preferably that you take the images at the same time of day. Usually that's not too much of a problem, but as you can see in the graphic to the right, where we have different shadows along a project from 8 a.m. in the morning to 4 p.m. in the afternoon. So if we took some images in the morning and some in the afternoon, that might cause problems. It at least would degrade the algorithm's ability to work with the images in DatuGram 3D. So what we'll be looking at today, and there are several examples of how to work with a camera for DatuGram 3D in the Datumate user guide or the DatuGram 3D user guide, but in this case I'm going to keep it strictly to the project that we'll be working on today. And this is a UAV intersection survey, and we'll be photographing the survey area from several angles, or you'll see that the photographs were taken from several angles, and there were a few ground control points that were measured, and that was done with total station using some using reflectorless methodologies, some with a prism, and certainly you could intermix GPS locations as well. So when we're surveying a junction or an intersection, basically what we want to do is take 20 to 30 consecutive images from the junctions or intersections perimeter, and we want to take those images every few meters. We want to keep the camera centered, so that'll be our focal point, if you will, centered on the center of the intersection. And we want to, again, as I mentioned before, these last two key elements, we want to elevate the camera above ground level to minimize obstructions, and we want to modify the elevation of the camera between images. So I'll show you the images in a little bit that were actually used in the project that we'll be working on. You'll see in this case they were elevated by using a UAV. We'll talk about that a little when we get to that point. The key thing to this is we want as many overlapping images as possible. There's a 50 image limit in DatuGram 3D, so we don't want to go over that amount, or we want to break it into individual projects if we need to go over that amount, particularly if we're doing a strip survey, which you can see at the bottom right-hand side. But this will make the automatic algorithms perform better because we'll have multiple images to find points on, and by having narrow angles between them, it just allows everything to work better and more accurately. So to achieve the optimal results, again, we're looking at least 20 to 30 consecutive images, and we have a couple, and we want to have overlap. I mean, 60% overlap is the recommended amount, but we'll likely have much more than that, and that's not a problem, and actually is recommended to have a lot of overlapping images. And we have a couple of concepts of how to work here to get those consecutive overlapping images. On the bottom left, we can see a building facade. Now that might be taken by standing there and taking pictures or on a pole, but you basically start at one side, work consecutively along the facade of the building, focusing generally on the center part of the building, except if it was a very long building, you might use a methodology a little more like the road shown on the right-hand side, where we sort of have overlapping pictures looking directly at it if it's such a long building. In the middle is what we'll be working on, is the intersection example, and again, just going around in consecutive order and taking many images. And on the right, which we will not be going into today at all, is a roadway, and there's some technique for doing that. You can see a serpentine approach where they start in the middle and go to the sides in sort of a serpentine formation. And if you can read it, I don't know how well you can see it on the screen or not, but it says strip 1, strip 2, and strip 3. And the strip 1, which is the sort of direct overhead shots along the center of the road, would be more appropriate if you were using a UAV, and you would likely skip that part if you were using a telescoping monopole, for instance. All right, so Let's talk a little bit about georeferencing the images. In the field, we want to be able to clearly identify control points that have no ambiguity to them and can be easily identified on the images. I think this is not at all different from what you've been doing conventionally with aerial photogrammetry, except we're looking at really high accuracy results, so we want very specific locations. So for instance, you would not necessarily want to try to use the center of a telephone pole, something along those lines, which might be more appropriate for something that was flown with very high altitude. In this case, on the left-hand side is a splotch of oil, not a very well-defined location, so you wouldn't want to do that. On the right-hand side, we can see a very clear and good contrasting arrow intersection where we can locate that in the field and see it on the photographs themselves. So we don't want everything on the ground, which I think you'll see in the next slide or two, but we definitely do want to use easily identifiable objects that you'll find in the field. And that could be corners of buildings, tips of arrows and signs, corners of window trim. I've used that pretty effectively. And there are generally a lot of objects out there, but occasionally you may have to put your own targets down. But we find that's a very rare thing that happens. Typically, maybe if you're doing something on a new building site where it's a lot of raw land around it, or if you're out in a very rural location, you may not have a lot of targets available, so you may have to create your own. We want to make sure that we measure our control points with the highest accuracy we can, at least the accuracy that you're expecting to get on your project. The moral of the story is that you cannot have more accurate results in any software, and this is true for DatuGram 3D. It cannot be more accurate than your survey control to begin with. So if you're looking for really high accurate results, then you need to have your surveying be high accuracy and your location of the georeferencing points or ground control points to be very and highly accurate as well. So as I mentioned before, it's very important that when you decide what to use for your ground control points to georeference the images, that we do a couple of things. And one of them is we do not want to clump them all together. We want to scatter that control around the images and the project to give it good constraints on the images and the area that you wish to survey. So we can see in the leftmost image all the ground control points, which I'm calling them ground control points, but not one of them is on the ground. But all the georeferencing or anchor points, control points, whatever you want to call them, they're clumped together. That is not going to lend itself to accuracy. Whereas the right-hand side, we've really spread out the control so that it's relative to the breadth, depth, and height of the image. And another important thing to keep in mind is that we want to have whatever we're going to be surveying within the control, not exterior to the control. Within the control, then we're interpolating correct results. If we go outside of the control, we're extrapolating results, and the further we get from the control, the less accurate those results are going to be. And lastly, I think the really important is to choose control points on more than one plane. So if we were doing a building facade, we don't want all the control points just on the face of that building on one plane. That would not be very accurate. If we were doing the parking lot, we wouldn't want everything on a very flat parking lot, all the control points. That wouldn't be very accurate either. So we want to vary the elevations and the depths if we're looking at a building, for instance, so that we're not having all our control points on one plane. That leads to very inaccurate results. Okay, so let's take a look at cameras. How does it work? We'll go into a little bit of the technology or math behind photogrammetry, and then I think most importantly, selecting a camera. So let's have just a little bit of a talk about measurement accuracy, because positional accuracy in close-range photogrammetry depends on a few factors. One of the factors, and clearly a key factor, is the camera resolution in megapixels. The higher the resolution, the better generally. The distance from the camera of the measured object. So even if we have a high resolution camera, we're going to be getting higher accuracies if the object that we're selecting in the image is closer to the camera's orientation and location than it is farther away. The accuracy of the georeferencing of the control points, which I mentioned before, we will not get better results than what your initial surveying control has for accuracy. And then, as I mentioned about angles, minimum angles between images. So if we have very large angles between images, that's not good. There's a slide coming up on this, but basically you want to think about this like resection, or even getting on real low technology and getting really accurate results with swing ties. We want good angles between them. So just to give you an idea, an 18 or better megapixel camera can get you 1 to 2 centimeter accuracy from a distance of about 150 meters. And again, that depends on those above items, whether you can, how accurately you're going to be getting your results. And a little bit about how this works. So what we can see here on the bottom left is an image, and there's a red dot marked XL. And so if we were to select that point on the image, because we know the focal length and radial distortion of the camera, and that's done through a quick calibration process, then we can calculate the math of that vector. And that vector lines up with, see if I can annotate this for 1 minute. If we can see over here on the right-hand side, there's a red line that I just put a yellow line over. Now I've deleted it. But that's the same vector as shown on that image, the second image. And that's called an epipolar line. And by finding the right pixel that is along that vector, we can determine where X is. Now, as a minimum mathematical requirement, all you need are 2 images, but DatuGram 3D requires 3 images to add a level of redundancy and a checking to the process. And as I mentioned before about the angles, so as I just mentioned, every point you measure must appear, at least in DatuGram 3D, on 3 images taken at different angles. And to get the best optimal measurement accuracy, we want the angles between the outside images orientations to be 90 degrees, and with the third one being directly in the middle, so that there's 45 degrees between the 3 camera locations. Now, in likelihood, and this is why we want more images in DatuGram 3D, you will have more images than that. But that's the minimum required, and that's the best geometry required. But if we infill with more camera images, all the better, because then we have multiple redundancies to measure any one point. So we have a question here. At 50 meters, would the accuracy be 3 times greater than at 150 meters? Now, I don't believe so. I'd have to check in on that. I think instead, what you can look at it as, there's a maximum error, if you will, for the camera resolution. If we just look at that one component, and obviously there are other components to this, but if we could narrow it down to just the camera resolution, that say we had a 20 or 24 megapixel camera, you can get 1 to 2 centimeters at, let's say, 400 feet. Obviously, it is more accurate closer that you get in distance, but I'm not sure that it's a direct correlation or not. But if we can keep within those limits, you get survey grade measurements regardless. I hope that answered your question. So a key factor here is that if we use a zoom lens on the camera, we do not want to change its settings while taking the images, because we've calibrated the camera with the setting, usually your widest angle that you have for the lens on your camera. And if we change that focal length by going out and changing the zoom, then all bets are off. The software will not be able to resolve anything. So what we recommend doing is getting a fixed lens. You can see at the bottom right is a 16 millimeter fixed lens if you're using a camera that will accept something like that. And that has a lot of advantages. So we want to use a high resolution camera. Better resolution allows higher accuracy. Recommended 18 megapixel or better, with the price differentials between an 18 and a 24 megapixel camera. My recommendation is, if you can afford it, to go to the 24 megapixel camera. We want to make sure we're using a lightweight camera, particularly if you're going to be mounting it on a UAV. And we want to make sure that the camera has a Wi-Fi built into it, which most new cameras do, because then it can communicate with your smartphone or your tablet to be able to use the smartphone or tablet as basically your viewfinder and snap the pictures. The other factor is we want to use a camera with a large CCD or CMOS sensor. The larger the sensor size, the better. We want larger than 100 square millimeters is recommended. I skipped over it a minute ago because I knew it was coming up, but we were talking about wide-angle lenses. It's a larger field of view, which gives you crisper images, easier calibrated, and your field crew cannot change it, or yourself. I've done it accidentally when I didn't have a fixed focal length lens. If you changed it, you're all done. So we want to keep it simple for the people in the field. So we recommend getting if it's the type of camera to do that, a 16 millimeter focal length or smaller wide-angle lens. Again, used fixed focal length lens. We cannot change the zoom characteristics while we're working on it. All right, so here are some recommended. These are the Datumate recommended cameras as of October 2014, just to give you an idea of what has worked very well and they've had good results. So there's the Sony Alpha A6000, the Samsung NS Mini, the Nikon 1J4, and the Panasonic Lumix DNC GM1. A good example was the first one on there, which is the Sony A6000. It's compact. It allows interchangeable lens so that you can get a 16 millimeter fixed focal length lens for it. And it's 24 megapixel resolution, and I've seen it, and the quality of those pixels are really very good. So it's a good camera to use for close range photogrammetry. All right, so now let's get into the DatuGram 3D itself. We're going to look at images, loading, and linking, which hopefully is done. So let me just switch screens here. Hold on 1 minute. All right, so I'm just going to show you, just for a minute here, the images themselves, because it's a little bit easier to see if we make them come up to the full size. So there are 19 images in here, and I've limited them to a smaller number just for the processing time alone. But you can see where It was done using a small UAV flying at about, 50 to 75 feet. Just went around the intersection with a fixed focal point, if you will, being the center of that intersection. Okay. And what I did, as I mentioned before, I just loaded those images on a new job. There's just a button in the middle that says load. You locate all your images, you grab them, it loads them right in. We do select a camera calibration that was for the camera that was used taken in the project, and then I clicked the link button, and then it ran through. So on my computer, these 19 images take about 13 to 15 minutes to link together, and they did successfully link into one cluster. If you have a hard drive, there's more read-write time involved, and it will take a little bit longer. Definitely not having a hard drive and having a fixed disk makes a big difference on it. The difference is that in older versions, or if it did not link successfully into clusters, let's say it didn't link into any clusters, we would have to anchor each image with 4 control points. But now that it's linked into one cluster, we need a minimum of 3 control points, but typically you'll probably be looking at 6 to 10 control points, and therefore not every image even needs a control point. So that, whether it takes 20 or 30 or 40 minutes to process your images can save you hours of anchoring otherwise. And if for whatever reason it had linked into 2 or more clusters, what you would see is below where it says that they're linked into one cluster, a button for a manual clustering, and we could link those together, the clusters, a little bit of a manual process of clicking identifiable points in the images, but not too bad to carry out at all. Okay, so this was the first step, was to link the images. Again, we're just looking at this mapping project. I just went over everything. But as far as the data goes, all we'll be using is the camera calibration, which I already applied, the 19 camera images, and you'll see in the next step the ground control points coordinate file. And very simple process. And this was taken with a 24 megapixel camera. Again, I mentioned flown on a small quadcopter, and ground control located generally with a total station. All right, so we went through the load and link. So the next step is georeferencing, importing control file, and anchoring the images. So as I mentioned, we need somewhere between 3 to 10 control points, and those ground control points, we need 3 of them to be shown in 2 images at about 90 degrees between them. The images, that is, need to be about 90 degrees between them, and then the rest don't have to follow that criteria. You can't see it, but I have a printed out copy of the images that is mocked up with the control points on it, and that's very helpful to have with you. Plus, Datumate has a new product out called Data Sketch, which will help with field sketches. We'll have more information on that to follow. And then as we go through the process here, I'm just going to show you a couple of tips and tricks on how to use your mouse to right-click to get menus to come up so we can rename, replace, or delete control points. Okay, so we're going to switch now to the Georeference tab. And the first thing, the software sort of walks you through what to do, but it says to import control points on the upper left. We'll click import. Go back to our raw data. So this is just a point, northing, easting, zenith file. We'll open that. There are some options for file types to make sure that it parses the data correctly. And make sure that you either convert the coordinate system that's used or the conversion from imperial to metric, or make sure that it matches what's already in set up for your DatuGram 3D job. So I'm already set up for US survey feet, which is what this file is set up for. So now what we can do is, it says over on the right here, there's a toolbar. Move it around so you can see it. It says start marking control points. Okay, so I'm working on the first image, and I'm just going to come in here, and one point that they used was point number 88. Now, first thing we want to do is turn on projections too, which won't come into play until we actually run the quality check, but it's good to have it turned on to begin with, and we'll show you what that does when it happens. But we want to turn on names too, so that we can see the names, and it makes it a little easier. Now, we want a minimum of 3 control points in this image. That will be shown on another image, 90 degrees different, those same 3 control points. In this case, I'm going to use about 5 or 6 control points. I'm going to mark them all on both images because, to be honest with you, almost all these control points show up in just about every image. So it's not a real challenge to find that. It works, and because of time constraints, we'll just set all our control in both images, run the quality check, and you'll see how it works. This one is 0.159. Now again, we're sort of boxing in the area around this intersection, but we also want to vary height. And this is point number 75, which is the top corner of a light, which is what, up maybe 20 feet. We can use the back side of this Crocs sign, is point number 93. We can use this crosswalk stripe. Just checking to see if we had any questions, which is 0.149. Let's just do one more. Let's pick corner of this window is point number 96. So we've marked 5 control points on this image. Now I'm going to switch a little bit more. I want to get about 90 degrees between the images. This one's fine. And we'll just mark those same points. Again, I need at least 3 that are the same points. In this case, I don't think it's a problem to do all of them. So that's 0.98. Tip of the sign. We'll try to go in the same order. This arrow tip is 159, which I looked away as I clicked. I guess I clicked OK. The top corner of the light is 75. The crosswalk stripe is 149. Now you'll notice that now I have a minimum amount of control. So I think it has to do with not only that there were at least 3 shown in 2 images, but that they were spread apart a little so they weren't all clustered together like these 3 first ones that I did. And the run quality control check button becomes active, and I could click that right now and run the quality control check. But let's just go in and add the other points, 93. And then what I want to show you is we know that the corner of this window is number 96. But let's just say by accident I called it number 95. Okay, so A couple of things you can do is there's a selection arrow. Let's just say, for instance, I had originally marked the wrong side of the window. So you can see you can just grab a control point and move it. But the other thing is I now recognize, oh, I punched in number 95. I want it to be 96. So we can do a few things. We can right click, and as I mentioned, that brings up some menus. And we could delete this point, and when you do a delete point in DatuGram 3D, you get the option to delete it from the entire job. But I think more appropriate for when you're doing your georeferencing, we can delete the mark from this image only, or the mark from all images, which is handy so that you don't have to look through every image if you realize you've marked something wrong. Or what we can do is replace control point with, we'll select 96 and OK. So I just wanted to show you that you have that ability to easily adjust and change the point numbers. Now, if I had put the wrong point number in, or had selected the wrong place on the image and run the quality control check, I am going to get, we use a red light, yellow light, green light system. I'm going to get a bunch of red residuals in pixels telling me that I have a major blunder. Okay, so let's just move it back. Let's run the quality control check, and it's going to go through the process. And what it's doing is it's comparing the survey control that you located in the field with what it's calculating on the images themselves. And let's let it run. And when it's done, it's going to come up with our marking accuracy on the right-hand side. So are there any questions at this point? And just to show you, while that's working away, let's look at the ground control post. So this was just the ground control points file. Nothing fancy, just a text file that I think everybody's familiar. It's got point number, northing, easting, and elevation. You'll see in the next step when we do measure and draw that we can select codes. And I think if you had codes in here, it will also, if it recognizes that codes as set up in DataGram, as you set up in DataGram 3D, it will apply those to the control points themselves. Okay, so that's just something you would go into your AutoCAD and export your control points and a point, northing, easting, elevation. I don't think it will let me do it while this is running, but we could do a couple of things, which on that drop-down menu, when you right-click on a point in an image itself, there was a properties dialog that will come up, which will show you information about that point. Description if it matches within DataGram 3D, the northing, easting, elevation, and the point number. We can also do that over on the control point screen on the upper left-hand side, which I know it's not going to let me do because it's processing right now. So let's just let it run. So it did not like that. Let's look at this first one again. I likely mocked something where I've done this particular project about 20 times and have never had an issue with it. So I see what I did right here. So I want to replace this control point. I put 98. It's 88. So there's a good example of, we can see that the errors, I'm just going to leave it for a minute. The errors at the right-hand side are in pixels, and it's showing red results. I knew I had done something incorrectly there, so that's actually point number 88, and this is point number 88. So I had marked that one wrong. So let's rerun that again. So it shows you really, and it will not let me move forward when we have red results. If we have yellow results, means that there maybe is a small marking issue, or maybe your survey control has some inaccuracies in it. We've seen that happen a few times where we've been able to find surveyors. I've got a question I'll answer in a minute. We found errors in surveyors' networks. So how much RAM do you recommend to run the software? you can go to, let's see if we can get it over here. If we go to Datumate.com, great website with a lot of resources available on it. But if you go to the Products DatuGram 3D page, System Requirements, good time to look that over. So these are the minimum requirements for it. So let's see, what do we have here? So it depends obviously on the system you're using. Minimum requirements are 2 to 4 gigabytes of RAM. They recommend 8. I think I have 12. I think I have 16. I typically never have a problem. It runs very quickly for me when I'm only running it on my computer. I've had Autodesk or AutoCAD going as well, and has not been too much of a drain. But for some reason, when we're running the webinar, the webinar software itself seems to slow things down. And having an SSD card instead of a hard drive really helps too. So there we go. So I made a mistake on marking one point. I rerun it, and we can see now on the right hand side that we have very accurate results, 2 pixels or better, and everything's green, and I can move forward. Now, in likelihood, and I'm going to draw a little, and then I'm going to open up another version of this exact project and show you some drafting I did on that. Actually did it just before the webinar. And on that one, I did go in and put some, I think about 3 or 4 other control points on other images. So I switched to, I think, like the second or last image and did a couple of control points, reran the quality control check, and I did one about 3/4 of the way through so that I had some control throughout the project. But for this example, I don't think we need to worry about it. Okay, so that's anchoring and georeferencing. So now what we want to do is we're going to switch to measure and draw. We're going to create 3D entities, and we can create points, 3D polylines, 3D polygons. We're not going to go over it in this webinar, but automatic topo point. And there's also a measure tool as well. All right, let's go to the next screen. And what it's doing now is if there were any new points in this, it's recalculating them, but it's georeferencing all those images and getting them set up so that we can start drawing. So the first thing you can do is go to Tools, Point Codes Library, and you can set up some point codes. Okay, I've set up a few. You can also import those. And you'll see up at the top of the screen here, as we click to new points, for instance, it comes up with automatic point numbering. We can select the point code that we want to use. I'm going to switch to stripes. We can create a layer on the fly. We'll call it stripes. We'll give it a nifty color. Make it purple. Okay. And then we can pick any image that we want to work in and just start drawing. So let's come in here. Again, we can do point, polylines, polygons, and this is a little bit faint. Double click closes that out. And they're white on this screen because this is the image we clicked on. But in the background, you can see on the upper right-hand side, it's saying it's automatically finding those four points in other images. And for each point that I click, when it finds that same location in at least 2 other images, you'll see that those will turn green. And we'll at that point have extracted a full 3D coordinate for that. And the line work in between those points will be full 3D as well. Okay, so we're waiting for one. And you don't have to wait. we could keep drafting while that's working in the background. So if we select this, so there's the object I drew. Let's just go back a couple of images. Okay, we can see that object is now projected correctly on the other image. So it doesn't really matter what image you start drawing in. You can just start doing the drawing that you'd like. Okay, and I'm going to show you a little bit more drawing, but let's quickly jump ahead a little. We're going to look just quickly at approving, checking your work. So, automation is great, and this is a great system for automating, creating a point by clicking on one image, but we want every surveyor to review and approve those results. And the key to this is approve and improve. Okay, we want to do both of those things. So I'm just going to switch to the approve screen for a minute. And here are those 4 points that I created. Okay, and we can see we're getting green results. Most of them are around 5 or 6 hundredths. There's one in the Y value is out 11 hundredths. Okay, and so one of these images represents where I clicked on the one image, and then the rest are where the software automatically found the same point. Okay, and so we can review that and say we're happy with these results, or we can come in and we can actually on the fly, and I'm going to change it quite a bit. It's a little faint, this paint stripe, but we can come in and we can improve the accuracy. I don't know that I'm actually doing that, but I don't know that I'm improving the precision of the results, but I know that I'm making it a much more accurate result because I'm adding redundancy to the measurements. And I would rather have many redundant measurements, even if they were slightly less accurate, than one measurement that was highly precise but very inaccurate. Okay, and part of this is a very faint thing. So it actually found it in every image. So we have 19 images that were used to create this point, and it just shows the accuracy or the redundancy there. And you can see this last one here, it couldn't see it because there's a building or something in the way. But if for whatever reason we don't like one of the images, we can just take it out by clicking the X on it and removing that image. So with that said, I'm just going to hit save here for a minute. And then what I want to do is switch to a job. It's the same job that I worked on for about an hour before this webinar and did exactly what you've just seen. The only thing different was I added about 3 or 4 control points on 2 other images. Can you draw a top of a curb and a bottom of a curb? Somebody just asked that question. So yes, and you'll see that right here. That's why I don't want to take the time, or didn't want to take the time out of the webinar to do the drafting, but I do want to show that to you. So you'll see that in a minute, Chris. All right. So let's go to measure and draw. This has already been anchored and linked. And so what you can see here is that I drew for about a little less than an hour, actually. And I think I picked this image here. And what you can see is I did draw tops of curbs. And you can easily see the bottom of curb here, too, if you want to draw that in. That's actually something that usually stands out very well. But I located some tops of signs or light posts, some of the crosswalks, paint stripes. Some of them I did individually. and some of them I just did en masse, sort of did the overall, which you can see in these areas. And so let's take a look at the last part of this is view and export. Okay, so we have a couple of view options for 3D and projection views. We have control point reporting, new points and topo points listings, and we can export reports in PDF format. We can also export in a DXF format, and we also can export point coordinate files. So we can take all these new points that we created and export that, and there's also an AutoCAD Connect feature. Okay, so we're going to switch to the view and export screen, and here you can see that it is getting 3D values, because here's what I drew. I actually started this about 1 p.m., so about an hour before the webinar, and let's see, I finished by almost quarter of, so it actually was more like 45 minutes. We can turn on the point numbers. Okay. You can see that that's full 3D drafting, that all these objects we created in points are three-dimensional. All right. The other thing is we can turn layers on and off. Okay. And we can also turn on meshes between all these objects if we wanted to do some modeling, if you will. There's also a projection view, which is basically a view looking straight down at the project. Again, what I really want to show you here is the control points report or listing. And so these are the control points that I used on this. So I had used 5. So I used 9. 5 when I first showed you, and this one I used 9. So I did add 4 more control points. And we're getting thousandths of a foot in residuals. Before we showed you it in pixels, you never work with that after the georeferencing page. So the difference between mathematically your control points that you located in the field and what was calculated using the images is thousandths of a foot. I think the highest value is 17 thousandths of a foot, and the lowest is 1,000th of a foot. So this is highly accurate. And on the bottom right-hand side, there's also new points and topo points listings. But at the bottom side, we can decide whether we want to include control points or not. We can export a DXF file. We can export a PDF report, point files. So if we export DXF, it exports all the layers and full 3D polylines and polygons and points for you to open up in your favorite CAD software to work with. And then what I mentioned before on the upper right-hand side is the AutoCAD Connect feature. So if you had AutoCAD 2014, you can connect this project with a drawing, and then whatever you draw on the measure and draw screen will automatically be shown in the CAD drawing, and vice versa. If you draw something 3D in the CAD, it will show up on the images, like I showed you that crosswalk stripe projected properly on other images. It will show up in DatuGram 3D. All right, so our hour is up. This is a revolution in digital photography that is changing the way land surveyors work. I didn't go over that too much, but largely because of what's happening with smartphones, that the ability to get these high accuracy or high resolution cameras very cheaply has come into play. And now we can measure and draw directly on images for the first time. And this allows with DatuGram 3D to turn a regular camera into a surveying and mapping tool. Datumate is the world's leading field-to-plan software suite. It makes land surveying works easier, faster, safer, and with superior accuracy. do visit. I showed it to you earlier, www.datumate.com. I do recommend going to their DatuGram 3D product page because it has a lot of great information on it. There are user manuals, there are case studies, there are the system requirements to review. It's a really great resource for you to look into. I want to thank you. I want you to join us for our next Datumate Live Webinar. Tentatively, we have that scheduled for February 26th. To be determined as to what the topic will be. If you have any suggestions, please feel free to email us. You can see the contact information at the bottom of the page for Datumate. You can email them at inquiries@datumate.com. Again, I'm Eric Colburn, PLS, President of Colburn Strategic Partners. I want to thank you for joining me today. I will stay on the line for a little bit. If you have any questions, I'd be happy to answer those for you. Just type them into the chat and we'll go over that. But at this point, I will wrap up the webinar by saying thank you, work smart, and be brilliant.